Good evening, everybody. I'm glad that you joined today's talk from Pierre Gembaczka about the topic AIfES, an open source standalone AI framework for almost any hardware. So first, some organization points we want to discuss. And the first of all, we want to thank every partner of the tinyML Foundation. So we want to thank Ion Devices, ARM, DeepLight, Edge Impulse, EMSA, Greenwaves, Gravity, HOTG, ImageMob, Latent AI, Maxim Integrated Analog Devices, Kixo, Qualcomm, Reality AI, Winesis, SAP, Seed, SenseML, SynSense, and Sentient. Thank you very much for your support. If you're interested to be a sponsor also, don't hesitate to contact Olga at tinyml.org for more information. So yeah, in the tinyML Foundation, we started a new series, the Trailblazer series. It's a series about success stories in tinyML field. So the first talk or interview will be with Feedforward on the 3rd September at AM Pacific time. You can register on the tinyML website or in the QR code here. Our next big event will be the tinyML Summit in 2020. So the summit will be in real life in San Francisco. The registration will be opened at the 15th December. And if you are interested to submit a poster, you have the chance until the 17th September 21. And yeah, the best product of the year and the best innovation of the year award are open for nomination between 15th November and February 28. If you are a researcher and interested to submit a paper, the submission for the paper for the call of paper is open until December the 17th. And yeah, if you need more information about the summit or the research symposium, you can go on our homepage, the tinyml.org. Other new series we started or the kickoff is already done is the tinyML for Good workshop. The kickoff meeting was on November the 17th. And yeah, this is a series about how to use tinyML for good things, to make healthcare better, to make a change in climate change and the earth, or to build up the STEM community. Our next talk will be on the 7th December from Chris Rogers from SenseML and Theo Kersey from OneSemi. The topic will be the value of Edge AI for industrial applications on SEMI and SenseML IoT solutions. Yeah, the webcast will start at 8 o'clock at Pacific time. To introduce our small German committee in the tinyML field. So we have 3 members in Germany. The first one is Carlos. He's a software project manager for IoT devices at Robert Bosch. Then we have Daniel. I think he can introduce himself.
Hello, everyone. So I'm Daniel from TU Munich. Now we are organizing this a little bit, and kind of what we are always interested in is if you have some ideas or if somebody is here who also would like to give such a talk. So this is kind of really organized very on demand. So we are talking to people, we are inviting people, but we are also very happy if you contact us with some ideas for a talk or a meeting, and then just really feel free to just get in touch with us.
Yeah, thank you very much, Daniel. And yeah, I'm the last member. I'm Markus Rüb. I'm a researcher in the field of tinyML, and I'm working as a researcher at Hans Schickert Research Institute. And yeah, like Daniel told us, or you, if you ever have an idea for a talk or are you interested for a talk, don't hesitate to contact us on LinkedIn, for example, or after the talk, and then we can pick up an appointment. So yeah, I'm really glad that we have today Dr. Pierre Gembaczka today in our talk. He is program manager at the Fraunhofer IMS, He studied microtechnology and medical technology and written his PhD at the Fraunhofer IMS Institute. And yeah, since 2004, he worked in the Institute for Micro and Nano Systems. And yeah, now he's the product owner for the tool AIfES, or for the framework AIfES. So Pierre, the stage is yours, and I'm really happy or glad that you're here.
Hello. Yes, thank you very much for the introduction, Markus. I'm glad to be here. It's very cool. And okay, I would like to divide my presentation in two parts. So the first one is the normal one. I would like to show you some slides and bring you into the topic. And at the end, I would like to show you something live. So this would be the idea behind this presentation. Okay, let's start. So what is AIfES? So AIfES stands for Artificial Intelligence for Embedded Systems. We have chosen a small f. So maybe it's a little bit confusing, but we have a small f in the middle. The cool story about it is that AIfES was a project of mine, a private project of mine. It started as a maker project, and which was pretty cool and pretty interesting. And after 1 year of programming, I started to do a pitch at the Fraunhofer IMS, and the guys was very interested. I said, okay, this could be very cool project for the Fraunhofer Institute. And now we are a team of researchers, PhD students, and students working on this cool topic. And what is AIfES? It's an open source framework for microcontrollers. And the cool thing about it, you can not do only the inference, you can do the complete training on your microcontroller. So it's a standalone framework for machine learning. And it's programmed in C, so you have no Python or stuff like this. And our vision from the AIfES team is that we would like to build intelligent and self-learning embedded systems. And our mission is we would like to do it very easy for you. So we would like to have an easy integration. And we would like to do the machine learning where the data is generated, so directly in your sensor, directly in your system. And what does tinyML or embedded AI mean for us? So I think this is quite the same. So we would like to do the AI directly in your sensor where the data is generated. This has a lot of advantages. So you have fast processing. You have increased security because you don't need any access to a cloud or web server or stuff like this. You have increased reliability because you are directly in your system. And normally when you have a small neural network or a small machine learning algorithm, it's saving resources and you need much less energy. And in our special case, we have the last topic, personalizable AI. So we are interested to build up sensors or systems which optimize itself to the application or to the user. And here I have some demonstrators for you at the end. And of course, what makes it so special, so we have many different cool solutions on the market. I think the most common is Edge Impulse, which is very cool. It is an end-to-end solution. So you put in your data, you have a semi-automatic model builder inside, and then the deployment on your system. And we would like to offer some kind of framework like TensorFlow, Keras, but in small and with limited functions. But you can use it as a real framework. And we are open source, so you can download AIfES, no problem at all. And you can use it directly in your C or C++ IDE. It's just code, so you can insert it. And you can develop your neural network on your target hardware. For example, when you go into Raspberry Pi or whatever, you can do it directly on your target hardware, or you can do it on your favorite framework for Python, and then import the network into AIfES, and then you can further training and stuff like this. And of course, inference and training. And it's completely in hard C coded, so we have made it completely compatible. And when you can compile C code on your system, you can normally use AIfES, which means you can use it for an 8-bit controller like the Arduino Uno, up to PC embedded Linux like Raspberry Pi or smartphones or stuff like this. So you are not limited to your system. And you can load and run different neural networks. So this is possible. So you can change your system during runtime. And you can import artificial neural networks from other frameworks. This is already possible. And how does it work? So it's just to have an overview. So you have the source code. It consists of header and source files. You put it into your project, you compile it, and then you can use it. So you have no application between this. So you have your well-known IDE where you're comfortable with and which you would like to use. And then you can integrate AIfES, or for example, you can build up a DLL for Windows, and then you can use it on directly on your whatever simulation tool or Visual Studio application, whatever, though everything is possible in this case. And how does it look like? So this is I call it now AIfES basic version. So this is a current version you can download right now. We hope that the update of AIfES will be released in the next weeks. These are the updates I would like to show you today. And the current version looks a little bit like the Python framework. So you have the layer it method. So you build up your different layers. And here, for example, this network is shown here in this case. And so you build up the different layers. For example, an input layer, a dense layer, then the activation function layer, the output layer, and the output function. And then you wrap everything together in one model. So this is done down here. And then you have your compiled model. And the difference to the Python frameworks are that you can choose where you would like to store your data. So where are the weights? Where are the temporary data for connecting for the calculation of the neural network? And we already using tensors in AIfES. So for the input and for the output data, we are using tensors. So it's when you're familiar with Keras, I think the basic version of AIfES would be very interesting for you. But it's C code, so you have no hard error management. So when something is wrong, like a memory pointer is not right or stuff like this, it's a little bit difficult to find the errors sometimes. But this is C, of course. And we have some hardware accelerator support. We're supporting the ARM CMSys DSP library. So normally all the functions are normal for loops, for example, to calculate the matrix multiplications. And the modern compilers are working quite well. So they're optimizing the loops inside of the algorithms. But for large networks, the CMSys library is very cool. So you can do the hardware multiplications. You can do the matrix multiplications directly in hardware. And for large neural networks, there's a huge benefit. And the other thing is we are working on our own RISC-V core. It's called iRISC from the Fraunhofer IMS. And there are some extensions, especially for AIfES, so some AI accelerators inside. And we're working a lot in the case of functional safety and crypto functions. So a very small core, very efficient AI applications and safety functions. So these are the topics of our RISC core. And how can you use it? So we have a very cool partner. We're working together with Arduino, and we have wrapped AIfES to an Arduino library. So the IDE is a little bit different to the other IDEs, for example, from PC or stuff like this. You have to put the header and the source files files in one folder. Normally they are separated, and in this special case they are together. So I think this is the only difference. And some functions, you know, from systems, for example, the printf function or stuff like this is not integrated in these version, but it has the normal functions AIfES normally has. And the cool thing is that you can directly download it from the library manager, and you can use it with every Arduino board or Arduino compatible board. So when your board works with the Arduino IDE, you can use AIfES. Some examples are for specific hardware types, but normally the basic version works for every hardware. And we have published it under the GNU GPL version 3 license. But the licensing I will explain in the later slides. And already you can use it on a PC. We have a tutorial online on Arduino Project Hub, where I explain how to use AIfES, the GitHub version of the Arduino version, how to use it on a PC. It's very easy. And some words about licensing. So we have a dual licensing model. So we are open source under the GNU GPL version 3 license. So for every maker, it's completely free. You can use it for your private projects, and free open source software when it's under GNU GPL version 3. And in a commercial way, you can use it too, but in this special case, you can buy a license from the Fraunhofer IMS, and then you are opened up. You don't need to put your software under the GNU GPL license. So the license is for per year, and then you have a different license, and then you can use it in your hardware and can sell it, and you don't need to put your complete software under the GNU GPL license. And our partners are Arduino, I have already mentioned. We are a partner of the ARM AI ecosystem. And one cool thing, the colleagues from the Fraunhofer AIfES, they had a project years ago with Google to build up the Open Roberta Lab. And Open Roberta is for kids to program robots. And it's a graphical programming. So you can, per drag and drop, you can build up your source code. And then you can deploy it on your robot. And we would like to, or we have a project to integrate AIfES into the Open Roberta Lab. And some words about the paid license. So what you get is, you get, of course, the complete open source version, but in a different license. And you get on top a Python model wrapper. So when you, for example, have a neural network in Keras or TensorFlow, we have an automatic wrapper who wraps your model to an AIfES model. And of course, Fraunhofer is big. We have currently, I have noted it, of course, could not be open source because some things are a little bit difficult to use because the IP belongs to Fraunhofer. So this is a little bit difficult. And for example, we have federated learning. This is one we at Fraunhofer IMS working on, so that many different IoT devices can train together. This works very well, and we would like to show in the next months some kind of a demonstrator. But already some use cases like handwriting recognition as an encapsulated module, or human detection, a complex gesture recognition system, or we have one Fraunhofer Institute where they are specialized on automated optimization of network architecture so that you can shrink your neural network. And the function overview, currently AIfES is very limited in what you get. Currently you get a full feedforward neural network support. This is the current state with floating points. So you can optimize, you can configure your feedforward neural network. You can do everything. You can decide how much inputs, how much layers you would like to have, how much outputs, your activation functions. We have included many different activation functions. And you have the SGD and the ADAM algorithm inside. And you have the normal training types like online batch, mini batch, and stuff like this. And this is the current state. And I have already been asked, how can I get a feedforward neural network from other solutions to AIfES? So this is very easy. You build up your structure and then you insert the weights, the trained weights. There are two methods. We have the so-called layered method. So you do it layer by layer. Or I think it's a little bit similar to, for example, TensorFlow Lite. You have just one single array and each weight is after the other. And the order is quite the same like Keras. So when you export your weights from Keras, you can directly insert it into AIfES. And yes, we hope that we have the update in the next weeks. And the update is pretty cool. So at first we have an easier API. So it's called AIfES. You only have some few lines of code to describe a complete neural network. So you can use the basic version if you would like to change everything in the layer. But you can already use the easier version to do it very easy and very quick. And the next thing is we can do a weight quantization directly in AIfES. So you can do it on a PC, for example, or directly on your controller. When you have your neural network in floating point weights, you can do the quantization of the weights directly in AIfES. So at the end, you have an Q7 quantization. So the normal weights of the layers are in 8-bit, and the weights of the bias weights are in 32 integer. And the point shifting is done completely automatic. So you don't have to care where the fixed point is. It's everything done automatically. And afterwards, you have a quantized neural network. And one interesting point for very small microcontrollers, now we have opened up the storage of the weights in the flash memory. So when you have a pre-trained network, a small microcontroller and only flash memory, you can store your weights in the flash, and then we can read the weights out of the flash memory. And of course, we have a ton of new examples. And currently in development is the complete ConvNet support for 1D or 2D convolutional neural networks, including training, and a tutorial for reinforcement learning. And the last slide, of course, for this case is this is the AIfES development, but the Fraunhofer IMS has much more. So we work together with companies, with firms, with partners to they have a special problem, and we make a project together, a funded project or whatever kind of project, EU project or stuff like this. And we help the customers from the concept to the first demonstrator. And the cool thing is that you have every time a backend at the end which works. So it's directly in the system when you, for example, have a machine or stuff like this or a sensor and you have hardware. Normally we can use AIfES for the specific hardware and do the special use case solution for the customer. And currently we are already working on an AIfES workshop. This is from the from Fraunhofer too. So we are working on that. We have a cool workshop for AIfES. So these are the first part. And Markus, I don't know, have you some questions maybe for me?
Yes, I have. Yeah, the questions come and come. So let's start with the first question. Does AIfES support quantization-aware training?
The quantization of the fixed network. So when you have trained the networks, you can do the quantization. This is the current state.
Sorry, I think your connection was bad for 1 second. Can you repeat the answer?
Okay. No, I have activated the VPN because the examples are in the VPN. So sorry for the delay.
Okay.
The.
Okay, I think this is the VPN connection. Okay, Pierre, you are muted. Must unmute you, and I think this was everything the VPN connection.
Can you hear me now?
Yes, now
Perfect.
everything works. Perfect. So please answer the question again. Sorry.
No problem. I think this is the internet connection and Corona and home office. So yes, currently it's not possible. So it's only possible to do the quantization of a pre-trained neural network with float 32. So this is the current state.
Okay, great. Thank you. Then the next question is, what is the benefit of weight quantization on the hardware? Will it not increase the latency of inference? Is it better to quantize the model before deploying it on the hardware?
Yes, of course. So you can decide. Normally, you would like to do the quantization on a PC. That's what I had already mentioned. So normally you don't do it on your controller, and normally we do it on a PC. So this is the reason why we have the tutorial for the PC, that you can do it completely comfortable on your PC and then port it to AIfES. So but we have a huge increase when we are working with integer multiplications. Depends on the hardware.
Okay, thank you very much. Then the next question, or maybe you can do two questions in one. So one question is, what is the inference FPS on Raspberry Pi or Arduino? Do you have there some numbers?
Oh, a benchmark is quite difficult. So currently not, but I have the live demo, so you can show how fast it is. But currently we have no benchmark against everything. So normally we have the benchmark for the customer things. So when we have a use case for a customer, special use case, then we are working hard on optimization. But for the basic instructions, we have no benchmarking at this point.
Okay, and then there's one question: how long does it take to train a network for image classification on the Arduino?
Oh, yeah, yes, of course. This depends on. So we have at this point we have no ConfNet, but we are working on it, and this depends on the size of the network. So currently we are working on sensor solutions like. I will show you some gesture recognition training on the system, or color detection, or currently speech recognition. I think we have one interesting project where we have not used a convolutional neural network, and this is pretty fast. I hope I can show you in the next weeks a demonstration video. Currently, I'm under NDA and I can not say so much detail. But I think a huge network on a microcontroller would be hard.
Okay, good. Thank you. I would say there come a lot of questions. I would say let's start the demonstration, and maybe a lot of questions will get answered by your demonstration. Or I'm pretty sure they will.
Okay. So let's start. I have here the Arduino BLE Sense. I think most of you know this board. It's quite cool. It has a ton of sensors on it. And I would like to start with the color recognition. This demo is already in AIfES included, so you can just download it and test it on your own. But I would like to show it to you. So the board is connected, and the interesting point is on it. It has an RGB sensor, a proximity sensor, and a brightness sensor. And we would like to do some color recognition, but the training done completely on the system. So we have the data acquisition at the first. So we have a training phase at the beginning. Then we collect data from the different objects, and afterwards the training, and then the classification. And for this, I have here 3 envelopes with different colors. And okay, let's start. Let's try to train and classify these different envelopes. So, okay. We start the serial monitor. Oh, so I hope you can see it. And everything works automatically because we use the proximity sensor. So we start with the red envelope, and voila, it's not bright enough. So I hope this works because we need a little bit more light. The second one was the purple one, and then the blue one. And the training starts in 3, 2, 1, and go. And the training is finished. And now we do the classifications. The first one was the red envelope. And let's do it for the red one. So 99% for the red one. The second one, I think this was the purple one. So let's do it. So we have 97%. And the blue one was the last. And now we have a color recognition. And this was a training directly on the Cortex M4. So I think it was easy peasy for the Cortex. And let's dive into what we see here. So at first I unplug the board because it's every time he has here some error message. So what we have seen here is we collect some training data, 5 measuring points each color. And here are the 3 colors. And this is just the launch for the training. Then here we see the loss. And here we see the truth table. So these are the labels. So this is the first color. So we have the label here 100 and trained is 100. So it's nearly up to really good training. And this is here the second color has the label 010, nearly with 0.99, very good training. And the last one here is the last color with the label 001. So this was cool. It works the first time directly. Normally when you have a live presentation, everything or a single point goes wrong. So the next thing is I would like to show you AIfES Express. So at first I upload the sketch, and during I upload it, I can show you the code. So this is a new version. So in this case, we train the XOR truth table. So this network looks like this. So this is a network, 2 inputs, 1 hidden layer with 3 neurons, 1 output. And let's dive into. So this is very easy. So we have 3 layers. So this define, and we have 4 data sets because we have in the truth table, we have 4 states, 0, 0, 0, 0, 1, 1, and so on. And because this is interesting for the tensors and for the network itself. And the first step is we have an unsigned integer array with the length of our complete layers. And then we only need to add the inputs and the neurons. So this is the description for the complete network. And we have activation functions, of course, and we have activation functions in the hidden layer and in the output layer. And this is what we've done here. We have an enum function directly built in AIfES. And then you can choose the different activation functions. And here are the possible activation functions you can use. And when we add, for example, here a layer, we just have to add the activation function. So this is the description. The next step are the weights. So we have one function for the weight calculation. So we have to pass the structure and the maximum amount of layers. And this function calculates the weights. But it's just for the double check because we have a pre-trained network here. And so here is the weight array. And now we pack everything together. We have one structure here. We have only the AIfES model parameter structure. We pass everything, the layers, the structure, the activation function, and the weights. And then the thing is finished. So this is the description of the complete network. And now we need some data. So these are the tensors. At first, the input data, these are the different states, 0, 0, 0, 1, 1, 0, and so on. And you can use, in this case, a 1D array or a 2D array. So it depends what you like to have. And the input shape is like the other Python implementations. So we have 4 data sets and 2 inputs. So this is the shape of our tensor. And then we build up our tensor in AIfES. And for the output, okay, we have only one output neuron. So we have 4 data sets and 1 output. We build the tensor with the data and with the shape. And here is at the end the result in this floating point array. And of course, the target data just for the checkup. And here is the function where the magic is done. So here's the inference. This function does everything for you. It allocates the memory, it inserts the weights, it opens up the network, it closes the network, and at the end you have the result. And you can do multiple neural networks. So I have an example where we have 3 neural networks with different configurations, and you just load the different weights and configurations. And during runtime, you can do so much inferences you would like to do. And at the end, we have an error handling. So when something goes wrong, for example, when you have not enough memory or you have the wrong input tensor shape or stuff like this, you have a feedback. And let's run it. Sorry, I must be a little bit faster because the COM port has switched. And now we can do here the inference. I just have to type inference. And here is the neural network on our board. So here is the input 0, 0. We estimate a 0, and this is the calculated output. So everything works. And now we would like to do some training. Let's open the training example. So for the training, I upload this sketch that I can show you the live training after my explanation. So we compile the sketch. So it's the same network, but now we have one different thing. Okay, it's trained from scratch. So this means we have no pre-trained network. We start with a blank network. We need some init weights and stuff like this, and we do all now on the board. So at first, we need some random seed. And in this case, we use the noise of an analog pin. So this is the first step, which is different. And the rest is here for the print and stuff like this. The first step is completely the same. So we need our structure, our activation functions. And now the weight calculation number is interesting because we can do here a normal array or here a malloc. This is, we have here 2 possibilities, whatever you would like to use. And here is the path of the data to our structure. And here is the example for a 2D array. So it's the same like the first one, but not here is it a 2D array. And we have the same 2 tensors, but we have the target data tensor. This tensor is the label for the training. So this is our expected data. And the next step is the weight initialization. For this, we have here a structure in AIfES. And currently, you can decide if you would like to do an init uniform between some values. We have here between 2 and -2. The Glottrod uniform initialization or no init. No init is interesting when you have a pre-trained network and you would like to do some further training. So we have here an init uniform. And then, of course, the optimizer, we can choose between Adam and SGD. The loss can be here chosen. Use the MSE for your normal stuff. And when you use softmax, I would prefer the cross entropy. And then you have the normal things like on every framework or stuff like this. The learning rate. If you would like to use the SGD, you can activate the momentum, the batch size. We do here a full batch with a full 4 data sets. The amount of epochs, this is quite high. I explain it later. And we can do some, this is pretty cool. This is very unique, I think. We have a print interval. So it's an encapsulated function. And for example, I would like to know after every 10 epoch, I would like to have a printout of the loss. And this is what we can do here. We can say, okay, I would like to have after every 10 epoch, I would like to have print. And the cool thing is I can describe my own print function. So this here is the function I have here already here. It must have this this structure. It must be a void. It has any name you would like to use, and it must pass a floating point number. And then you can do whatever you would like to do. In this case, we have a global counter, which we add, and we plot the loss. So whatever you would like to do, you can do it. And the next thing is we have an early stopping. You can activate early stopping and give a target loss. And when you have the print epoch time, so when you go to the printing, internally AIfES checks, does we have reached the target loss? If yes, it stops training and everything is fine. And this is a function for the training itself. Error handling for the training if something is wrong with the memory or stuff like this, and then the inference. And okay, let's run it. So I have to switch again the port. I don't know. This is quite. This is only at the at this board that after the flash it switched the port. I don't know. And now we can do a training. So it's completely randomized starting point. So I hope it works. Okay, it works. And normally we have a total amount of 1,000 epochs, but we reached at 190 epochs the loss. And now we have here a live trained neural network. And the result is pretty cool, and it was very fast. So this was the training. And last but not least, I have a special one for you before I do something else. I would like to do some gesture recognition. So I open, I have 2 more demos. I hope I can make it in the time. So the first one is for the BLE Sense. It's a simple gesture recognition. So maybe you have seen it. I think it was for from TensorFlow for microcontrollers. They have shown on the BLE Sense some kind of easy gesture recognition. You have to train it in TensorFlow and then to port it with TensorFlow Lite and then on the board. And you can do, for example, a flex or a punch or stuff like this. And in this case, we would like to do everything on the board. So you don't need any PC in this case. And it's inspired by this demonstration. And I'm in contact with, maybe you know him, Eloquent Arduino. He has done some cool projects, and he had a simple gesture recognition based on support vector machines. And I have asked him, hey, can I use your kind of data collection? Because this was very cool. It's just a collection of the accelerations. And but I have asked him, it's cool, can I use it? And he says, hey, oh, of course, no problem. And now we have a neural network based gesture recognition. This is the one I would like to show you here. So we have the first sketch is for the data acquisition. So we have here the X, Y, Z accelerations. And we have some kind of threshold. So the gesture must have some acceleration to start it. So it starts automatically. You don't need to push any button or stuff like this. And it collects again 5 samples, each gesture. And then it's done the training. But in this case, we have the early stopping on. So like the example before. So we have here, this is a built-up model code, and this is here the training. It's exactly the same like before. The only difference is that the network is larger. So this is the only differences in this case. Okay, we have done an upload. This is a little bit tricky because I have to be careful with the device. So I put now the board in my hand and I start the serial monitor. I hope you can see it. So repeat gestures, and at first I would like to do a flex. 1, 2, 3, 4, 5. The next is a punch. 1, 2, 3, 4, 5. And the last is a slide to the left, a very hard slide to the left. Okay. And that's it. This was a training, and now I can do the classification when I do the, now it works. Or a punch, or a slide to the left. And this is a gesture recognition with training directly on the system. And the thing is the same. So at first you have here the features. We have 20 features in this case, and at the end the labels for the gestures. And then the loss for the training, we only need 100 epochs, and afterwards we have the sum up, what we expected and what we have. And I think I have some time for the last. Yes, I have the time. Okay, so the last one is very cool. We have some multi-core training with the portenter. So the basic idea was, normally when someone says, okay, let's do some tinyML, what with the core? So when you do training, the core is blocked and you cannot do what you ever would like. But the new boards, for example, the portenter H7, has a dual core microcontroller. And the idea was, we can do the first core for the normal stuff, and we have a second core for the training. So no core is blocked. Let's do it. And after the updates, you will have this demonstrator. So I now plugged in the portenter, and let's communicate with him. So start the serial monitor. COM port is now COM port 13. Let's communicate with him. And he says, okay, we have some comments here. And you see we have two LEDs on. We have the blue and the green LED on. So each core has its own LED. And now let's start with an inference. And the M7 says, oh, my network is not trained. And when I say, okay, do the training, the M7 says to the M4, hey, starts training. The M4 does the training, and here is the result. This works not very good. So let's do a reset. Okay. Now start again. So it's live training. I see, and now we have done. Okay, so now we have the first training was with a learning rate of 0.05. Here we have bad luck with the weights. So here was no training success, but here after 240 epochs, we found this, and we can do now further training. So let's do the training again. And now he starts training and he lowers the learning rate. Now we have a learning rate of 0.01. And he says, okay, everything is fine. And now we can do with the M7, the inference. And now the M7 can do the inference. So we have a dual core application here. And it works very fine. And it's only one sketch. And here the M4 does the training and the M7 does only the inference. So, okay, this was the live demonstration of AIfES. I hope it was okay, and I hope you can understand me. Sorry, I have not so much time, so I have to hurry a little bit. So yes, this was the live demonstration.
Great, thank you very much. Yeah, if you can go to the slides, please, then we can finish. But therefore, we have some questions.
Oh,
yeah,
yes, of course.
Thank you very much for your presentation. You know, I'm a really big AIfES fan. The half of the GitHub issues come from me or my team.
Yes, so, yes. We are really proud that you help us with AIfES. So this is very cool. Thank you very much in this case, Markus. So
you helped me for my PhD. So yeah, let's go to the question. So the next question is, when can we expect the ConfNet update?
The ConfNet, yes, of course. So I think we have we are now have the basic instructions for the ConfNet are already finished. I think in the middle of the next year, I hope we have the full support. So because ConfNets are, we have to implement everything from scratch, and the kernels from the ConfNet, the pooling layers are a little bit different. But we would like to support the ConfNet at first, and afterwards some kind of recurrent neural network and stuff like that. I think the recurrent neural networks are quite easy in this case because we have the feedforward neural network. But I hope in the middle of the next year we are finished with ConfNets.
Okay, great. Thank you. Then there are 3 questions. I want to cluster them. So yeah, microcontrollers are limited in terms of resource. And why do you train them on, or why should we train on embedded devices and not train them in the cloud or on host computer and upload it directly in the controller? And when you train on the device, do you have some optimization, automatic optimization in terms of number of, to compromise the model, number of neurons or hidden layers or whatever?
So the first point is, why should I train on a microcontroller? So the first thing you have seen, it does need so much time on the microcontroller. So when you have we call it a gray box model. So when you have expert knowledge and you have a good model, a strong model, which works, you can do it completely on the controller. But you can feel free. So you have the opinion you can use AIfES, for example, as a web application, and then download the pre-trained model to your system. The IoT devices can train together. This is the federated learning part. And I think it depends on what you would like to use. When you, for example, in an industrial or medical application, it's very difficult to send training data to the internet. And I think this could be the next big thing for medical applications, because I think this is a big thing. And when you, for example, do some kind of unsupervised learning, this is a mix of unsupervised learning and supervised learning, because you have a strong model, you have tested it on a PC. I think the color recognition and the gesture recognition, I have pre-trained with many different gestures. I have trained it and I have a good model set up. And the training at the end, you have already seen, it doesn't need so much time. And I think the application and the thing you would like to do with it. And I think industrial or real-time applications or medical applications, in this case, it's really cool to have this feature. And the training algorithms are currently the normal training algorithms, but we have some very fine implementations for the activation functions. So we have a very, very fast softmax implementation. And these are the kinds of accelerators we use. So we use the special hardware components. And especially on our own RISC-V, we are doing the activation for functions, for example, in hardware.
Great, thank you. Yeah, I'm really on your side when it comes to why we should train on embedded devices. Data privacy, or if it doesn't have any connection, I fully agree with you. Then the next question is, so apart from the on-device training, why should we use AIfES over TensorFlow Lite or Micro TVM?
Okay, I think this depends on you. So it's just a different solution. So I have already mentioned we have some cool solutions when it goes to only do the inference. So I think in this case, AIfES is limited when you look at other solutions. But in this case, we have 2 advantages. The first thing is, of course, you can train on your device. And it's not limited to the microcontroller. For example, when you use a smartphone, you can use AIfES too, and then you have much more power. And with the current applications, you can only do the inference. So just not only think in the microcontroller way. So we have smartphones, which has tons of power. So I think it's the McLaren for us to work on it. So I think in this way, AIfES pretty cool. When you have some special implementations or you would like to have very easy or stuff like this, I think, so after the update, it will be easy to use AIfES but it's C. I think in Python it's easier, but we plan to do some kind of Python implementation that you can use AIfES in Python directly, and then use it on your controller. So it depends on you. So when you're familiar with it, use the other solutions we have on the market. But when you go to smartphone or stuff like this, or microcontrollers, you would like to train on it, I think AIfES could be a good choice.
Okay, great. Thank you. And now the last question. Are the implementations of the training algorithm based on CMSIS neural networks if running on Cortex-M?
No, we only have the accelerators for matrix multiplications on. So when we use the ARMS CMSIS DSP library for the Cortex controller, we have only the matrix multiplications on. So normally, but this is the interesting part. When you have a small network, the compiler has a good strategy to optimize your code. So it's very fast. And when you have a huge network, then you have the benefits of the CMSIS or of the hardware accelerator itself, because it needs some time, it needs some ticks to feed the hardware accelerator. And they do a huge ton of multiplications in one step. But when you have a very small network, you don't have any benefit in this case. And yes.
Okay, good. Thank you very much. So this was all of the question. Then let's go to the end of this meetup. And
I have added some demonstrators and some projects. It's just for afterwards you can download the presentation, or you have the video, and then you have some further informations. But okay, I'm running out of time.
Yeah, thank you. This is great. So for everyone else, if you want to have the slides, you can go on our forum, and there will be the slides uploaded, and then you can check out the examples. Yeah, good. Thank you very much for the more points and the examples. Okay, I go through this, Pierre. I hope this is okay. Good. Yeah, here the contact data from Pierre. If you're interested to get in touch with Pierre and get more information about AIfES, everybody, if you can contact him. If you are interested in a double license model, yeah, don't hesitate to write him or call him. So in the end of the presentation, we want to thank every sponsor again, like in the beginning. And yeah, especially we want to thank ARM, the Software and Hardware Foundation for tinyML. We want to thank DeepLight. They use AI to make other AI faster, smaller, and more power efficient. We want to thank EdgeImpulse. This is tinyML for every developer. We want to thank EMSA, the eye in the IoT, Edge AI visualization sensors. And we want to thank GreenWaves. They enable the next generations of sensor and hearable products to process rich data with energy efficiency. Then Gravity Inc., the software development service for tinyML solutions. And HOTG, the distributed infrastructure for tinyML apps. Latent AI, the adaptive AI for intelligent edge. And Maxim Integrated, they have a lot of advanced AI acceleration ICs, low power Cortex, M4 micros, and sensor and signal conditioning. Quixo, AutoML, an automatic machine learning platform that builds tinyML solutions for the edge using sensor data. And Qualcomm, they're advancing AI research to make efficient AI ubiquitous. Then Reality AI, add advanced sensing to your product with Edge AI and tinyML. And SensiML to build smart IoT sensor devices from data. And yeah, SensiSense, with them you can build sensing and inference hardware for ultra low power in sub-milliwatt embedded mobile edge and edge devices. And Sentient and end-to-end deep learning solutions for tinyML and Edge AI. And yeah, thank you for every sponsor and for the sponsorship that we can run our group and the foundation. Our next talk will be on Tuesday, December 7th, from Chris Rogers from SensiML and Theo Curzons from OneSemi, and about the topic, the value of Edge AI for industrial applications. The webcast will start at 8 o'clock Pacific time. So yeah, thank you very much for joining the talk. I think this was a really interesting talk, and yeah,